Bismillah ar-Rahman ar-Rahim. Assalamu alaikum dear students. I am Mr. Kadim Khan and I am a lecturer in the Institute of Computing, Guwahati University of Science and Technology. Today we will take lecture number 21 of the subject of Introduction to Computing, in which we are going to discuss the conversion of number systems, where we will discuss octal to binary conversion system and octal number system to the decimal number systems, and at the end we have the octal to the decimal hexadecimal number systems. Dear students, this is the third lecture of the conversion of number system. In the first lecture we have discussed the conversion of binary number system to all these number systems, and then in the second lectures we have discussed the conversion of the decimal number systems to the other number systems. And now here we are discussing the conversion of binary number system to the octal decimals and the hexadecimal number systems. So this lecture is also very much important because these lectures contain some numerical or empirical questions. So you need to solve all these questions when you have to convert one number system to another number systems. This is the discussion agenda. It contains the topics of octal number system. So first we will explain what is the octal number system. Then we will explain the application or usages of the octal number systems. And then how we can represent the octal number system mathematically or diagrammatically. Then we have the conversion of octal to the binary number systems. Then we have the conversion of octal to the decimal number systems, and then we have the conversion of octal to the hexadecimal number systems. And each of these three conversions will be provided with the help of the practical examples. So here we will provide you some empirical examples how these number systems are converted to another number system. And of course, at the end we have some important references. These are the book references which you must have to study here. First, what is the octal number system? As its name indicates, the octal number system has the base oct. That means oct means 8. So octal number system have the range of 8 digits. So unlike the decimal number system, which has the range of 10 digits, that is 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9 and 10, that is 8 and 9 up to, but here in the octal number system we have the 8 digits from 0 to 7. So 0, 1, 2, 3, 4, 5, 6 and 7 are the numbers which in fact is used to create the octal number system with the base 8 number systems. Now the main characteristics of the octal number system is that there are only 8 distinct numbers are the digits, and these digits are from 0 to 7, with each digits having the 8's value of just 8, starting from the least significant bits to the most significant bits. It means that our first digits will be the in fact most significant, and the rightmost will be the least significant. For example, here 27237 to the base 8 is an octal number system. Here 2 is the most significant while 7 is the least significant digit or bits in this octal number systems. So the maximum value or the number in this octal number system is 7 and the least one is 0 here. So this is the number system which is very much important for us when we program the computer systems, while, for example, to provide the instructions to their processors. Now, where is the octal number system used? The octal number system is used in the earlier computing. Means that when the earlier inventions of the computers, then the computer system was using the octal number system. So at that time, the octal number system was very much popular for the counting of inputs and outputs. Means that here to the computer we provides input in the form of the octal numbers, and the computer also produces the output in the form of the octal numbers. And it was in counts of 8. So here in the octal number systems, the maximum number is 7 and the minimum is 0. So every time counts in the maximum to say 7 is in fact the octal number system. And here when the system provides us the output as well in the form of the 8, for example a byte at a time, so then we use the octal number system. Here the byte is in fact the memory size which represents the octal number. So in the byte, 1 byte there are 8 bits, so that's why these memory locations are mostly represented with the help of the octal number systems. Octal number systems are widely used by the systems such as Universal Automatic Computer, that is in short UNIVAC 1050. This was the first digital computer which was in fact invented, and that computer was using the octal number systems. So this was in fact the first digital personal computer which were used for the personal applications, and most purpose of this computer was to perform the arithmetical operations of the data. So that's why, because here the input was in and output was provided in the form of the octal number system. So that's why UNIVAC 1050 was a first computer that was using the octal number system. Another example is the program data processor PDP-8. So PDP-8, that is program data processor, was also another computer that was utilizing the octal number system. Similarly, International Computer Limited ICL 1900 was in fact a mainframe systems which were using the octal number systems. And of course, the International Business Machine, which has employed 6-bit, 8, 12 bits, 24 bits, and 36 bits. So all these were using the octal number system. For example, in the 24 bits, that was in fact 3 multiplied by 8. So that is, and every 8 bits was in fact called bytes. So this means that there are 3 bytes in 24 bits. Similarly, in 36 bits words, there were in fact 4 bytes, that means 32 bits, and then next 4 bits were in fact the signed bits. So these are in fact different computers which were used in the past, and these computers were classical computers which were based on the octal number system. Also, the octal number systems is in fact the abbreviated from the binary for this machine, because the word size was divisible by the 3, and by the 3 means 2 power 3 is equal to 8. So that's why here the word size was divided by the 3, and each octal digit represents 3 binary digit pairs. So octal number system has a vast applications, and still the current computer, that is now our personal computer, also using the octal number system. This is the representation of the octal number system. As the octal number system has base 8, that means that there are maximum 8 digits in the octal number systems, and the first, which is the least significant bits are the digits, is 0, and the most significant value is the 7. So 0, 1, 2, 3, 4, 5, 6, and 7. All the numbers are in fact comprising with the help of these 8 bits here. Now here is the representation of the octal number systems. For example, 0 means nothing. So in the octal number system, 0 means nothing here, and it is starts, every number starts at 0. This is the 1 instance of the circle, so it is the 1. Similarly, 2 instances means 2, and so on. And up to 7 instances here means that we have 7 different different types of circles. And after 7 there is no 8, but that is after 7 there is directly 10 here. but 10 is in fact the 8. So 1 0 represents the 8. So start backs it's 0 again, but add 1 zeros to the left. So starts backs is 0 and also added 1 to the left of this 0. So this is in fact 8. And this is 9 in the decimals, but here in the octal it is 1 1. That is 11. And this is 12, but it doesn't represent 12 here because this is in fact here 0, 1, 2, up to 7, 8, 9, 10. This is 10, which is 2 less than 12. And so on. After 16, we have 17. And after 17, we have no 18, but it is 20. But these are not 20 here. These will be 18. And similarly, this is 21 after 20. So and so on. So this is the representation of the octal number system here. Now here we will perform some important conversions. First conversion is the octal to binary. So in this first conversion, we will convert the octal numbers to the binary number systems. The algorithm used to convert the octal to the binary numbers have these 3 steps. First, take the octal number as an input. So we will consider any octal number as an input. Then we will convert each digits of the octals into the binary. We can also use the table here, but we can also convert any octals by binary when we will in fact divide it by the base of 2. So then it will be converted to the binary, and then the output, that will be the output to the binary number system. Now here is the examples here. So we need to convert the octal number 540 into the binary number system. So according to that algorithm, we will convert this octal number, which is 540, to the equivalent binary numbers here. So first take the input, that is 540 to the base 8. When we in fact here divide all these 540 into 3 different digits, 5, 4 and 0. So 5 is 101, similarly 4 is 100 and 0 is 000. Now remember that you cannot exceed 3 bits here because 2 power 3 is equal to the base 8 of the octal. So that's why we will take 3 bits isolate in the isolations. So this is the conversion of these octals to the binary. Now we will combine all these bits here. So 10 11 00 000 to the base 2. So this is the conversion of the octals to the base here to the binary. Now I will in fact perform arithmetics here, how we have converted that 540 to the binary. So here we will perform 3 different divisions. So first we will divide 5 by 2. So for example, this is the division here. For example, 5 divided by 2. So 2 2s are 4 and remainder is in fact here 1. Now divide this 2 by 2. So we will get 1 and remainder is 0 here. So our equivalent binary, when we convert 5 into binary, so we will get 101. This is 101. So here this block is in fact the output of these bits here. So this is 101. Now again, when we convert 4 to the binary, so we will perform the division here. So we will divide 4 by 2. So here you can see 2 2s are 4 and 0 is the remainder here. Again we will divide 2 by 2. So 2 divided by 2, this is 1 and 0 is the remainder. So here In fact, when we divide 2 by 2, 1 is the quotient and 0 is the remainder. So our required octal number is 100, which is here, this one. This is 100. Similarly, 0 by 2 means 0. So we will here represent 3 different bits, 000, because the base of the octal is 8 and 2 power 3 is equal to 8. So we require 3 bits here. So 000. Then we will combine all these bits. Then in fact here it will be 1011000000. So this is in fact here, which we have converted to the binary. This is conversion of octal to the binary. Now here is another example where we will convert that into the binary. So for example, if we have the word or the value to 352.563 into the binary numbers. So according to that algorithm, so we will split this octal number to the individual digits 352 and 563. So we will divide this 3 by 2. So when we divide 3 by the base 2, so we will get 011. When we divide 5, so it will be 101, and when we divide 2, so it will be 010. Then point, when we divide 5, so we will get 101, and similarly 6, we will get 1100, and 3, so we will get 011. You can also use the table here, but the better is the previous techniques. The previous technique is this one that we have already demonstrated here in this example. So you have to do it through yourself so that you will get practice. So when we combine all these bits together, so the output will be 111010.1011110011. So this is the required octal to the binary. The next is the conversion of octal to the decimals. In the decimal number system, we have the base 10. Means that there are 0 to 9 digits in the decimal number system, but in the octal we have 0 to 7 digits, so that means this has the base 8. So in the octal number system, each digit position has the weight 8 according to the power 8 shown in this figure here. So 8 power 3, 8 power 2, 8 power 1 and point, then 8 power minus 1, 8 power minus 3 and so on, etc. So this is called the octal points, and this is the most significant values, and these are the least significant values here. Now, how we will convert the octal to the decimal systems? There is a very simple procedure. So, for example, we have 304 to the base 8 is equal to unknown decimal number system. Then we will take 304. 304 is equal to 3 multiplied by 8 is about 2. Because this 3 has the position of plus 2, and then we have 0 multiplied by 8 to the power 1. So because 0 has the second positions here and second most significant bits, so it has n minus 1, that is 3 minus 1, and in fact here we will take it to 0 multiplied by 8 to the power 1 plus 4 multiplied by 8 to the power 0. So starting from the least significant, then we will in fact increment its base power from 0 to onward up to n minus 1. So 4 multiplied by 8 power 0 plus 0 multiplied by 8 power 1 plus 3 multiplied by 8 power 2. So conveniently you need to first specify the highest most significant bits, that is 3, which has 8 power n minus 1, that is n is here 3, 3 minus 1 is equal to 2. Then for this n is equal to 2, so 2 minus 1 is equal to 1, and from here n is equal to 1, so 1 minus 1 is equal to 0. So overall, when we resolve this expression, so we will get 196 here. So 196 is the equivalent of decimal numbers to the octal number 304 to the base 8 here. Here we will resolve second examples of the conversion of octal to the decimals. So in this example, for example, if you take 125 as a octal numbers, so we will denote it 125 to the base 8. So 125 to the base 8 is equal to 1 multiplied by 8 raised to power 2, because there are three digits in this input 125. So 3 minus 1 is equal to 2 plus 2 multiplied 8 raised to power 1, because we have three digits, two digits after this. So 2 has the value here, uh, that is the 100 digits. So this will be n minus 1. So 2 minus 1 is equal to 1, plus 5 multiplied by 8 raised to power 0. This is equal to, in fact, because 8 raised to power 0, because 5 has the most significant value is 1. So 1 minus 1 is equal to 0. So 5 multiplied by 8 is 0. When we will resolve this expression, so initially we will get 1 multiplied by 64 plus 2 multiplied by 8 plus 5 multiplied by 1, because anything which has the power 0 is equal to 1. So when we resolve all this expression, so we will get 64 plus 16 plus 5. So 64 plus 16 plus 5 is equal to 85 to the base 10. So this is the, in fact, an examples which converts the octal to the decimal number system. And you are also expect such questions in the exam papers where you have to convert the octal number to the decimals, and remember that you have to convert it into step by steps. When you will convert, for example, 125 to the base 8 is directly 85 to the base 10, so you will not get any marks here. So you need to perform all these arithmetics step by steps here, so then you will get good marks here. Dear students, the next conversion is the conversion of the octal to the hexadecimal systems. You know that the base of the hexadecimal number system is the 16, and that hexadecimal system consists of the numbers, alphabets, and it is represented with the base 16, because there are 16 bits digits in the hexadecimal number system. Now look at here how we can in fact represent the hexadecimal number system. So all the hexadecimal number systems has the number from 0 to 9s, and these are represented in the visual forms, but after 9s there is no 10s to 15, and it is denoted as A, B, C, D, E, F. So we will not use 10, 11, 12, 13, 14, 15. We will use just A, B, C, D, E, F. Because when we will use 10, 11, 12, 13, 14, 15, so that is not hexadecimal system, that is in fact decimal number systems, because in the decimal number system we have 0 to 9, so 10 is in fact 1 0, which is in the decimal number, and 1 5 is also under decimal number system, which is comprising from 1 and 5. So A, B, C, D, E, F are in fact the characters or alphabets which denotes 10, 11, 12, 13, 14 and 15 here. The conversion of octal numbers to the hexadecimal number system requires two steps. There is two-step methodology used to convert the octals to the hexadecimals. First, we will convert octal number to the decimals. So in the first step, the input octal number will be converted to the decimal number system, which we have performed in the previous steps. And then we will convert that decimal number system to the hexadecimal number systems here. So after converting the octal to the decimals, then the intermediate value, which is the decimal value, will be converted to the hexadecimal number here. Now here is the examples how we will convert the octal to the hexadecimal number systems. For example, if you want to convert 55 to the base 8, that is 55 to the base 8 into the hexadecimal number system, so first we need to convert it into the decimal number system, then decimals to the hexadecimal number system. So for example, 55 to the base 8 is equal to 45. How we will get 45? So first 5 multiplied by 8 is equal to 1 plus 5 multiplied by 8 is equal to 0, because there are two digits 5, 5. So first digits has the base 8 to the power 0, and second will be multiplied with the base 8 to the power 1. So 5 8s are 40, and 5 multiplied by 1 is equal to 5. So 40 plus 5 is equal to 45. So we have obtained 45, which is the decimal number system. Now we will convert 45 to the hexadecimal number system. So here we will perform this division method. So for this purpose, we will take the input, which is 45, and we will divide that by the 16s, which is the base of the hexadecimal system, until we get the remainder, which is less than 0, 16 in fact. So 45 is divided by 16, so 16 twos are 32, remainder is 13 here. Now we will divide, when we will divide 2, so we cannot divide that. So that will be in fact 2 13. Or when we divide 2 by 16, we will get the quotient 0, and remainder is here 2. So we can also stop our division up to this point. So 2 and 13. 2 is in fact the quotient, and 13 is the remainder here. But 13 is equal to the D, because we have no 13 in the hexadecimal. We have A, B, C and D values here. So A for 10, B for 11, C for 12 and D for 13 here. So therefore we can write 45 to the base 10 is equal to 2D. 2 is this remainder first, and 13. You can also take this 0, so 0 to D will be the output, but you can write 2 13 instead of 2D. So 45 to the base 10 is equal to 2D to the base 16, or 55 to the 8 is equal to D. 55 was the original number, which is was the octal. So 2D to the base 16 is the output here. Now here is, in fact, we will perform another examples. This is another example when you want to convert 125 to the base 8 into hexadecimal. So first we need to convert 125 to the decimals. So 125 to the base 8 is equal to 69. In fact, how we have obtained the 69s. So 1 multiplied by, this is the 1 multiplied by 8 is equal to the power 2. Then we have 1 multiplied by 8 to the power 2. So this is the first bit, 1 multiplied by 8 to the power 2, because there are 3 bits overall up to this position. So 3 minus 1 is equal to 2. When we convert 2 to the decimals, so we will 2 multiplied by 8 to the power 1. Similarly, 5 multiplied by 8 to the power 0. So when we will resolve this expression, we will get 8 multiplied by 8 plus 2 multiplied by 8 plus 5 multiplied by 1 is equal to 85. Now we have obtained 85. Now then in the second steps, we will convert 85 into the hexadecimals. So we will use this division methods here to convert this octal to the hexadecimals. So here 16 by 85, when we divide 85 over 16, so 16 fives are 80 and 5 with the remainder. So up to this position, our division is now completed. So required hexadecimal number is 5. So as this remainder is less than 16, so here our division has been completed. So required hexadecimal number is 55 to the base 16, or 125. 8 is equal to 55 to the base 16 here. Now dear students, you can also perform the cross-checking of all this conversion. So for this purpose, I want to open the calculator of the window. So just launch the calculators of your window. So here is the calculators that I have launched here. So then I will in fact open the slides here. If you have already the standards window of your calculator, so click here and go to the programmers here. So when you will click on the programmers menu here, so this will be in fact programmers menu here. Now we want to convert 125 to the hexadecimals, and 125 is the octal number. So we will click on octal here. and then type 125. 125 in the hexadecimal it is 5555, which is here. So that means that our calculation was in fact pinpoint accurate, and it is equivalent to the decimal 85, which was here 85, and to the octal of course 125, and to the binary 01011001. So this was how we have converted that into another format. So by just you can use this calculators to check that how you have performed these operations. Again here we will validate this conversion 352.563 to the base 8. So here, because this is octal number, so I will click on the octal. Already our octal is selected. So first I will in fact delete the previous inputs. Now 352 is in fact the octal number. So when we convert this 352, so it to the required binary number, it is 1101010. So this is 1101010, and similarly 563, that is we will here delete this. This is then 563 to the required binary number is 1011111, but these 3 bits is in fact is used for the first 3 bits, which is the in fact octal. So you have to eliminate first 3 bits here, which are 0. So the required output is 1011111. So this is the cross-check methodology to your calculations here. So this is in fact the final slides, and this is the end of the lectures. And here is the book reference for you. The book is the Binary, Octal and Hexadecimal for the Programming and Computer Science, written by Sunil Tanna. So you should download this book and you should read this book for all sort of conversions here. And if you have any question, you can ask the question through the email m.kadim@redcast.edu.pk. Also, if you have any problems, you can in fact ask to resolve such problems through this email ID. I will wait for your questions and any of your queries, and I will in fact answer you immediately as soon as I will get them. Thank you very much.